Alright guys, so in this video we're going to start talking about the graphs of the other four trig functions. And what we're going to say is the graphs of the other four trig functions are really determined in the same way we determine the graphs for sine and cosine, right? So we're going to say that ordered pairs for the graphs of these other four trig functions are going to be determined by x values that are rotations from standard position and y values that are ratios given to us by the x and y values on the perimeter of the unit circle where those rotations end. When we look at the ratio of cosecant, we have 1 over the y value where that rotation ended. And so that's what's going to determine the y values of the ordered pairs of cosecant. Now, right here, when we're looking at the ratio as 1 over the y value, there are some rotations for which the y value is 0. In fact, what we can say is any rotation that lands us on the x-axis is going to have a y value of 0, right? In general, we can say that's going to be integer increments of pi, right? We would say 0 pi, pi lands us on the x-axis, 2 pi lands us on the x-axis, 3 pi would land us on the x-axis, and so on. So in general, right here, what we can say is that any rotation that is an increment integer of pi will land us on the x-axis, giving us a y value of 0. And when we divide 1 by 0, we're going to say that we get a vertical asymptote. So in general, right here, what we can say is for the graph of cosecant, we are going to see vertical asymptotes for rotations that land us on the x-axis or at integer increments of pi, right? And what we're going to do now is just go around one rotation on the unit circle and talk about what we get at each quarter rotation for cosecant. So right here, we start out with 0 radians of rotation, and what we can say is we've got that y value of 0 giving us a vertical asymptote to start with on our graph of cosecant. As we rotate to pi over 2 in a quarter of rotation, we see the y value is 1, and we would get 1 over 1, or 1 as the function value, at a rotation of pi over 2. Rotating to pi, a half rotation, we would see a y value of 0, and that of course would give us a vertical asymptote halfway through one period of our graph of cosecant. As we rotate 3/4 of rotation, we can see a y value of -1, which is going to give us a function value of -1 when we divide 1 by -1 at a rotation of 3/2 pi. And then finally, as we rotate to the positive x-axis with a full rotation, we get a y value of 0 for a rotation of 2 pi, ending us on a vertical asymptote. So right here, what we're going to do is go ahead and look at the function of cosecant as we rotate around the unit circle. And we're going to basically look to see what's happening with the y values on the perimeter of the unit circle as we rotate through each quadrant. So at 0 radians of rotation, we have a y value of 0. Our cosecant ratio is undefined since we're trying to divide 1 by 0. As we rotate through the first quadrant, though, we see the y values increase. And we start out dividing 1 by very, very small y values for small rotations, giving us very large function values for cosecant, right? And we can basically see that as we rotate through that first quadrant, those y values will increase to 1, giving us a function value of 1 at pi over 2, right? As we rotate through the second quadrant, we're going to see those y values decrease back to 0, meaning that the function values for cosecant are going to go up to positive infinity as we approach that vertical asymptote halfway through our cycle, or halfway through our period. So right here, rotating through the second quadrant, we're dividing 1 by smaller and smaller numbers, and that makes our function values go up to positive infinity. Rotating through the third quadrant, we are going to start out with very, very small negative y values. And when we start dividing by very, very small negative y values, we see very large negative numbers for our function values with cosecant. So right here, we're coming up from negative infinity with the graph of cosecant as we rotate to 3/4 of rotation to 3/2 pi. And right here at 3/2 pi, we've got a y value of -1, which gives us a function value of -1 when we divide 1 by that -1. As we rotate, we see those negative y values on the perimeter of the unit circle recede back to 0. And that means that we are going to be dividing by smaller and smaller y values, taking our function values down to. And so this is basically what one period of cosecant looks like. And so right here, graphing cosecant, we can basically see it as a function that sort of loops down to local mins between vertical asymptotes and loops up to maxes between vertical asymptotes. So between our first two vertical asymptotes, we can see our function come down to a local min and then go back up to positive infinity. And then between our second two vertical asymptotes, we see our function values come up from negative infinity to a local max and then go back down to negative infinity. And of course, because as we rotate around and around, we see the same y values on the perimeter of the unit circle, just like sine and cosine, we can say cosecant is a cyclic function and its cycle is just going to repeat. So right here, if we extended out on the negative axis, we would basically see the repeat of that cycle, where basically from -2 pi to negative pi, we see our function dip down to its local min, and then between negative pi and 0, we see our cosecant function come up to its max and then back down to negative infinity. Now right here, we're going to do a quick analysis of our cosecant function. We're going to say that the domain is all real numbers, and we're going to write real numbers as this R with a line through it. That's the symbol that means real numbers. And we're going to say that the domain is all real numbers except those rotations that land us on the x-axis, which are the integer increments of pi. So right here, we're going to say except for x equals k pi, where k is an element of the integers. As for our range, the y values in our order pairs, we're going to say that the y values come up from negative infinity, and they top out at that local max of -1. And we're going to say that we don't have y values between that local max of -1 and that local min of 1. Our y values pick up again at 1, and they go up to positive infinity. And right here, as far as symmetry goes, we can say that our graph of cosecant is an odd function, not bounded since our function values go up to positive infinity and down to negative infinity. As far as extrema go, we can say we have a min of y equals 1 at x equals pi over 2 in one period of rotation, and we can say that we get that same min for every coterminal rotation, which means that we will see that same min at every integer increment of 2 pi. So we would say 2k pi plus 2k pi would give us basically every y equals 1 min for the graph of cosecant. As far as maxes go, we can say that we have y equals -1 as a local max, and that happens at x equals 3/2 pi in our first period. And then right here we can say that it's going to happen at every coterminal angle again, so we would say plus 2k pi, where k is an element of the integers. Finally, right here we can say that as far as asymptotes go, we again get them wherever we have a y value of 0, which are the integer increments of pi, the rotations that land us on the x-axis. So right here we can say x equals k pi, where k is an element of the integers. So right here, what we're going to do now is go up and define one period of cosecant. I'm erasing a little bit of my graph here. You guys don't erase the graph. You guys should have more paper, so you should be able to fit this in. But right here, we're going to say that cosecant as a function starts at a vertical asymptote. At its first quarter, it has a min. The halfway point, we can say that it goes into another vertical asymptote. In quarter 3, we can say that we hit a max. And finally, we can say that the graph of cosecant ends with another vertical asymptote for one period, right? That's what one period is going to look like. All right, guys, so what we're going to have you do now is go ahead and try to come up with a graph of secant on your own. And what I want you to do here is to go through and look at all the quarter rotations and look at what we're getting for the secant ratio at each of those quarter rotations, right? So basically right here what you're going to do is go through, evaluate the ratio of secant at each of the quarter rotations, right? Mark that off on your graph. So right here you're looking at rotations from 0 to 2 pi, a full rotation. And what I want you to do is think about what's happening to the x values in the ordered pairs as we rotate through each quadrant and see if you can come up with what the graph of secant is going to look like. We're going to stop the video here and we're going to come back and look at that graph of secant and then do some quick analysis and write down the period.
All right, guys, so we're going to look at the graph of secant here. Of course, we're talking about a function that is determined by x values of rotation and y values that are given to us by the ratio of 1 over the x value at the end of that rotation on the unit circle. So right here we start out with an x value of 1 for 0 radians of rotation. And as we rotate through the first quadrant, we're going to see those x values decrease to 0. So basically right here, we're going to see those x values decreasing to 0, giving us function values that get larger and larger as we divide 1 by smaller and smaller numbers, going up into a vertical asymptote that we see at a rotation of pi over 2. And right here at pi over 2, we have a denominator of 0. And if I landed that rotation right on the y-axis, we would basically see that secant would be undefined, as it is right now. I'm just really, really close. Right here we can say, rotating to pi over 2, we have an x value of 0, which makes the function of secant undefined. That ratio of 1 over x is undefined. Now right here, rotating into the second quadrant, we start out with very small negative numbers. So the graph of secant is going to be coming up from negative infinity, because when we divide by very small negative numbers, we get very large negative numbers, and so function values are going to be coming up from negative infinity. And as we rotate through that second quadrant, we see those x values come to -1, and that right there gives us the ordered pair pi -1 halfway through the period of secant, right? Now rotating through the third quadrant, we're going to see those x values get less and less negative, receding back to 0. And as those negative x values go back to 0, we're seeing the function values get really more and more negative. And those function values go down to negative infinity. And when we rotate to 3/2 pi, we have an x value of 0, giving us a vertical asymptote at 3/2 pi. And now rotating through that fourth quadrant, we start to see very, very small positive x values first. And then those positive x values get larger and larger. And of course, this means that we're coming from positive infinity on the other side of that vertical asymptote at 3/2. We're coming down to an ordered pair of 2 pi 1. And so that's roughly what our graph of secant looks like. As we look to analyze this graph,
we want to remember that just like the graph of cosecant, the graph of secant repeats, because of course as we rotate around and around the unit circle, we are cycling through the same x value. So right here with the graph of secant, we're basically seeing that same period repeated over and over again, right? Just like cosecant, we're seeing a domain of all real numbers except for the rotations that will give us 0 x values on the perimeter of the unit circle. So right here, basically we can say that those rotations are any rotation that lands us on the y-axis. So right here, we first land on the y-axis with a rotation of pi over 2. But from there, what we can say is any integer increment of pi is going to land us back on the y-axis. So we can say that pi over 2, or any integer increment of pi, will be a rotation that lands us onto the y-axis, giving us an x value of 0, where our function would be undefined. The range of secant is the same as the range of cosecant, so that's negative infinity to -1, including -1 as a local max, union with 1 to positive infinity, where we say that that 1 is a local min. We would say that the secant function is even. It has a min of 1 at x equals 2k pi. So basically right here we're saying that min of 1 first happens at the beginning of our interval, and we see that min of 1 happen again at the end of our interval. So right here we can basically say that it's going to happen at the ends of the interval, which are happening at integer increments of 2 pi. Right here we can say that the max we have is -1, and that happens first at pi, and then it's going to happen at the same point every period. So that means that it's going to happen at every coterminal rotation, and those are integer increments of 2 pi again. So we would say 2 plus 2k pi would give us every x value that would give us a max. We can say that the vertical asymptotes for secant are going to happen for rotations that land us on the y-axis. So again, we can say that that's pi over 2 plus an integer increment of pi that would land us on the y-axis. And right here, that would be the rotation values or the x values that would give us vertical asymptotes for secant. Right here, we want to go up real quick and determine one period of secant, right? So when we're talking about secant of x, we say that we have a function that starts at a min, right? And that's the local min we're seeing right there. In its first quarter, it goes into a vertical asymptote. Halfway, we see a max. That's the local max we're seeing right there. In its third quarter, we are seeing a vertical asymptote again. And then finally, it ends back at that min. And so that is one period of secant. All right, guys, so we're going to stop the video here, and we will look at the graphs of tan and cotan in the next video.